Welcome to the last video of Unit 2 where we talk about free fall. So we're going to be talking about gravity for this one. If I drop two balls, a ping pong ball and a steel ball, which ball would fall faster? If I demonstrated this in grade 10, then you know the answer. If not, we'll demonstrate it in class. But as long as the balls are similar in size and not dropped over an extreme distance, they will fall at the same speed because they're both affected by the same value of gravity. But this is different from what we might observe for different objects. So if you drop a sheet of paper in a ball, the paper will definitely fall slower. And that's because of air resistance. Now, way back in 350 BC, Aristotle would experience these phenomenons where lighter objects, things like paper and compared to a heavier object like a rock, fell at different speeds. So he connected that to being proportional to mass, or the weight of the object, which took a long time for somebody to disprove which was in 1590 by good old Galileo Galilei, where he said that objects fall to the earth with the same constant acceleration if there's no air resistance, and it's air resistance that changes how they move. And he demonstrated this in a lot of different ways, dropping objects with different mass, same shape, different shape from different heights, and came to this conclusion. So what does it mean to be in free fall, this thing that we're going to be studying this whole time? So free fall is the movement of an object that is only, and I'm going to underline that because that's really important, affected by the force of gravity causing it to accelerate uniformly. Now, the whole caveat to this is that there's no air resistance, which we know isn't a true situation. Everything that we drop on Earth travels through the air, so there is some element of air resistance no matter how aerodynamic our object is. We're ignoring that this year. We're just going to pretend that all of our problems have no air resistance so that we get to understand how the motion is occurring. Eventually, when we talk about forces, both this year and next year, we'll be able to include the air resistance factor into our problems. But for now, just assume no air resistance. Some of the best ways to think about, how consistent gravity is to look at some examples. Now, we're going to go through this in class, but if you take a minute or two to try and draw out these two graphs for two situations, then you'll be prepared to start our discussion in class. So, a position velocity graph, two sets here. Use a pencil. On the right one, try and draw what it would look like if a ball was dropped on the left side here. So if you're just dropping a ball and it's falling towards the ground, we're just trying to think about what those two graphs would look like. And then in the other side, so on the right side, we're going to do slightly different, but very, very similar. We're going to have a ball tossed up first. So it's tossed up and then let fall back down to the ground. So it would be at the same points as the ball dropped at the end. So it goes up and then down. So try and draw those graphs, and we will go through those in class, and also we'll go over these acceleration time graphs. Now, these are not something we do very often because they're very, very simple. They don't tell us a lot of information, but it can sometimes help us realize how consistent gravity is. So we'll do those in class. Let's get to some numbers and some calculations though. So gravity. is g equals 9.80 meters per second squared. Now, if you remember, I might have said 9.80 last year in grade 10. This is why, because it has 3 sig figs. So it's all about foreshadowing year by year by year. So 3 sig figs for gravity. You'll notice that I didn't put downward or negative. That is all part of our direction now. We're not just saying that g itself is negative. G is just the number. That is how fast things are accelerating because of gravity. And based on our problem, we will choose which direction is positive and negative so that we either end up with a positive g or a negative g in our problems. We'll see 2 examples that will do one each way in a few minutes. It is less at the top of the mountain and more at sea level, and it is also less at the equator. And we can see that in these 2 charts here, which are interesting to look at, how as you go from the equator north 15 degrees latitude, you're gaining a stronger value of gravity. So you would accelerate faster and feel heavier as a result as well at the North Pole than you would at the equator. And same thing if you're at the top of Mount Everest compared to being at the Dead Sea. Now, the interesting things here with that all come from the equation that affects gravity, and it's all about how far you are away from the center of the Earth. But you'll get into more of that with forces. So let's do some problems. Most of our problems, everything up is positive as normal. We'll do one in a moment that is down becomes positive because it just makes our life a little simpler. So you've got a ball thrown upward with an initial velocity of 20 meters per second, and we're calculating the final velocity at these 2 separate times. So v naught equals 20.0 meters per second. Up is positive, so A is negative g, which is negative 9.80 meters per second squared. And we're looking for v. Now, our simplest equation that has these 4 variables would be v equals v naught plus at. Now, when we're doing free fall problems, you'll notice that I'm not putting vector arrows, and that's because we're only working in one dimension. We're never going to have other directions, so positive and negative, you don't need to worry about writing our vector arrows for gravity problems. So plug in our numbers, 20.0 meters per second plus 9.80 negative meters per second squared times 1.00 seconds. Some easy math here. 9.8 times 1 gives us negative 9.8 with the same sig figs. 20.0 minus 9.8 will give us 10.2, and that will be the proper sig figs. So 10.2 is our final velocity after 1 second. Now, I'm not going to rewrite our givens because they're exactly the same for part B. Now, let's just jump into our equation and calculate it and see what happens and see what's different between these 2. Everything is the same, except we're no longer 1 second in, we are 3 seconds in. You plug this into your calculator, and you should come up to negative 9.4 meters per second. Now the key here is to think about what the positive and negatives mean. A positive velocity means that we're moving up, and a negative velocity means we're moving down. So after 1 second, if we've thrown the ball up with a velocity of 20 meters per second, the ball is still moving upwards. It's slowed down quite a lot, but it's still moving upwards. However, 3 seconds after we've thrown it, it has gone up to its maximum height, stopped instantaneously, and then started coming back down and increasing its speed, and so it's on the downward part of its motion. What is the ball's velocity after 4.08 seconds? Okay, so I'll just rewrite the givens here quickly. V naught is 20.0 meters per second. A is negative g, which is negative 9.80 meters per second squared. and our time is 4.80 seconds, and now we're looking for our displacement. Well, let's just go to our displacement equation that has V naught A and T, which is V naught T plus 1/2 AT squared. Now we're going to plug everything in here, 20.0 meters per second times 4.08 seconds plus 1/2 times negative 9.80 meters per second squared times 4.08 seconds squared. Don't forget to square that time at the very end. Number one mistake that will happen. Now I'll show some intermediate numbers here, so you will get 81.6 meters for this first part with sig figs to the 6 minus 81.567 meters in the second one, and again sig figs would be 3, so sig figs to the 5 there, which if you see that would round to 81.6. We just put the numbers straight as they are though in our calculator. 0.03 meters is going to be our result, which our sig figs, if we're doing addition, they should be rounded to 1 decimal place, and if we were to round this to 1 decimal place, we get 0.0. So what does that tell us about our object? It's back where we threw it from. So 4.08 seconds later, it is back at the initial height. So, knowing that, the problem to solve in next class will be how far has it traveled in total distance in that time. So see if you can solve that, and we'll go through that in class. Let's take a look at a problem that involves theme park rides. So rides like Drop Zone, where you get dragged up and let go from the top of the tower and you free fall and you're strapped in, all just work because of gravity. But because the motion we're looking at is only downwards, we're not going up, we're not looking at the up part, we're just looking at the down, we can choose down to be positive. So in this case, our initial values are time equals 2.0 seconds, acceleration equals positive gravity, just because we're saying that down is positive. Just because if we don't have to deal with the negatives, why bother? And we're looking for how far would we fall. Again, our most used equation, V naught T plus 1/2 AT squared. V naught is 0, so this part goes to 0, so we just have 1/2 times 9.80 meters per second times 2.0 seconds squared, which you plug that into your calculator, it'll give you 19.6 meters. But we should only have 2 sig figs because 2.0 is only 2 and we're doing multiplication, so we should only have 2 sig figs, so it'll round up to 20, but we have to rate it as 2.0 times 10 to the 1 meters. So there's our final answer. Now that number being positive, we have to remember that we said down was positive, so that means that we fell 20 meters from that height in 2 seconds. Now what was the final velocity after 2 seconds? So we're just going to look at V equals. Now the best equation to do this with, again, V, we have V naught, we have A, we have T. Well, let's just go straight into V equals V naught plus AT. Again, this is 0, so it's just 9.80 meters per second squared times 2.0 seconds, which is 19.6 meters per second out of our calculator. And again, V will have to be 2.0 times 10 to the 1 meters because we have 2 sig figs and we can't have 20 because that would only have 1. So 2.0 times 10 to the 1 meters per second. You've got one more problem there that you can work on, and we'll go through it in class. That's the end of Unit 2, and so that means we can expect to be working on a lab soon and a test. And as always, physics is awesome.